Hi everyone, welcome back. Let's write some more Leetcode today. Today we are solving remove all occurrences of a substring. So the problem states that we are given two strings, s and part, and we want to find the leftmost occurrence of the substring part and remove it from s. And we want to continue this operation until all the occurrences of the substrings are removed, and then we can return s. So if we look at these examples, in example 1, we see the first occurrence of ABC, so we remove it, now it looks like this. And now this is the second occurrence of ABC, remove it, now it looks like this. And then now we remove the last occurrence of ABC, so now S is DAB, and that is what we return. In example 2, we see the first occurrence of XY looks like this. And then we remove the next occurrence, now the string looks like this. After removing the next occurrence of xy, now it looks like AXYB. And finally, the resulting string would just be AB. So now that we have seen some examples, let's get to how we can solve the problem. For the brute force approach, we can set up a while loop that will continue iterating as long as the substring part is in string S. And at every iteration, we want to find the index of the first character at part, and then we want to remove the entire substring from S. And then we continue doing that until all the substring part is removed from S. And then we can return the resulting string. But the kind complexity of that would be n squared divided by m, where n is the length of S and m is the length of part. Because the while loop is already n time, and then removing the substring is another n time, so that'll make it n squared. And then we will divide that by m, because every time we remove, the string may become shorter by m. So there is a more efficient way to solve this, and I'll get to that right now. So a more efficient way to solve this is we can set up a stack. So first we'll initialize an empty stack, and then we will write a for loop that will iterate through string s, and at each iteration we will add the character to the stack. And whenever the last few characters in the stack is equal to part, then we need to remove the part from stack. So like right here, for example, ABC right here is equal to part ABC, then we need to remove all of these from stack. And then in the end, we will just return all the characters that are in stack. So the time complexity of this would be n times m, where n is length of s and m is the length of part, because we will have to iterate through string s, and removing m from the stack can take up to m time. So it would be n times m. So there is still a more efficient way to solve this problem, and we'll go over that one right now. Before I go over this method, I would recommend looking up the KMP algorithm if you haven't. Otherwise, it'll be really hard to understand this method. If you search this on YouTube, there should be some pretty good videos about this algorithm. They can probably explain it much better than me. So I recommend watching those videos rather than having me explain. But I will be going over this example using the KMP algorithm. So let's go over it right now. So first we will have this LPS array, which stands for longest prefix suffix. So for this problem, it wouldn't matter too much, but let's say if part is A, then this would be 1, telling us that when we're looking for pattern and we are here, we can just start at index 1, because after A, what we need after is B, so might as well just start here. But for the Leetcode example, it doesn't matter too much. Also, we will have a stack to keep track of the characters that we add to the stack. And then we have s index, which stands for the index at s, and part index, which is the index at part when we are iterating. These will be the index that we use to keep track. And then we will also have this patterns array to keep track of the stack if we can skip certain steps. Yeah, I think it'll make more sense as I go over the example. So let's go over the example right now. So at first, we will add d to stack, but we compare s of 0 to the part of 0. They are not equal, so we don't do much besides we need to increment s by 1. Now we compare s of 1 to p of 0. A is equal to a, so we need to add a to the stack, and then we also need to change this to 1. It will be right here and not here, because that's just how KMP works. You add the index by 1, and we also need to increment s index and part index at the end of iteration. Now we compare s of index at 2 to part index at 1. They are not equal, so we need to decrement part index back to 0. So s at index 2 is equal to part at 0. So we need to update pattern and add a to the stack. So now s of index at 3 is also equal to part of index at 1. So we update patterns and then we increment these two indexes again. So what these patterns are telling us is basically, so at 1, a, basically we can just start at part of 1, and if we are here, so if we look at patterns, we can just start at part of index 2, so we can skip some repetitive steps. So now we add C to the stack and we compare these characters. So C is equal to C, and we realize that part has reached the end, so we can remove these from the stack and update patterns. And we look at A, so it's 1, so we should just change part index to 1 and increment S index. So now we add B to the stack, and S of 5 is equal to part at index 1. So we need to update patterns at here, index 2 or index 3 in patterns, because it will be the index of stack plus 1. S of 6 is not equal to part index of 2, so we need to reset this back to 0. So now we compare S of 6 to S of 0, and they are equal. So we add A to the stack, and we need to update patterns and increment S index and part index. Now, S of 7 does not equal to part index of 1, so we need to reset part index back to 0 again. Now we compare these two, so A is equal to A. We need to add A to the stack, update this to 1, and increment part index and S index. Now at 8, it is equal to at 1, so we need to add it to the stack and update the patterns to 2 over here and increment the indexes. So at 9 and 2, they are equal, so we add C to the stack, and we notice that the last 3 elements in the stack, it matches part, so we can pop these and update patterns. Now we increment S index again, and part index, we set it back to 1 because A tells us to set it to 1. It's DABA 1, 2, 3, 4. Now we increment S index again, and part index, we set it back to 1 because A tells us to set it to 1. It's DABA 1, 2, 3, 4. We compare 10 to index 1, they are equal, so we need to add it to the stack and update patterns again and increment the indexes. So now finally, we've come to the end. Compared to C, they are equal, so we add them to stack and update patterns once again, and then we need to increment the indexes. And since ABC also matches ABC over here, we can pop from the stack again. And now the S index is equal to the length of S, so we can end the iteration and return the characters in stack as our result. So the result for this would just be DAB. Time complexity of this problem will be O of n plus m, where n is the length of S and m is the length of part. And the space complexity will also be O of n plus m because of the patterns array that we're making, and LPS, which it could be the length of part. So now let's get to the coding part. Okay, so first I'm going to set up the helper function. We're going to call it longest prefix suffix. That's how we make the LPX array. I'll be using this function. So self and pattern as the parameters. So LPS is 0 times the length of pattern, and I will be the index. Prefix length was set to 0, while I is less than the length of pattern. If the pattern of I is equal to pattern at the prefix length, then we need to increment the prefix length by 1. And we need to set LPS of I to prefix length and then increment I on its own. Otherwise, if the prefix length is not equal to 0, then we set the prefix length to the LPS of prefix length minus 1. Otherwise, we just set LPS of I to 0 and increment I. And finally, we can return the LPS. So now we will define the LPS as self.longest prefix suffix of part. And we'll initialize the empty stack, the patterns, so 0 times length of S plus 1. And the string index and part index will both start at 0. So while string index is less than length of S, we will continue iterating. So that will be our while loop. And we'll set char, the character, to S of string of index, just to make the code simpler. And we will append char to stack at every iteration. And now, so if the character is equal to the part of character at part index, then the patterns at length of stack, we will increment part index plus 1. and part index, we need to increment that by 1 on its own. And if part index is equal to length of part, then we can pop it from the stack. That means we have found a substring. So for I in range length of part, stack.pop. And we need to reset the part index by looking at patterns. So 0 if we have an empty stack. If not, then the pattern's at the length of stack. Okay. Else, if part of index does not equal to 0, then we need to subtract the string index, and part index would be the LPS of part index minus 1, and pop from the stack. Else, then we just set patterns of length of stack to 0, and at each iteration we need to increment the string index by 1, and afterwards we can return the result. So empty string join stack, let's see if it works. Okay, perfect. Hope this was helpful. Thank you all for watching. If you have any questions, feel free to leave in the comment section, and I hope to see you all again soon.